Okay, this is going to be our day 2 notes. We're going to start out with a warm-up, very similar to what we did. We'll review what we did last class on day 1. We're going to graph the function y is equal to log base 2x. And remember what we talked about last class, that whenever we're going to graph a log function, we're going to set up a table of values and fill it in the y values first. So let's set up a quick table of values over here on the right-hand side. Fill in our y values for -2 and -1, 0, 1, 2. And remember that y equals log base 2 to the x is 2 to the y is equal to x. That's why we fill in the y values first. 2 to the -2 will be 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4. We can plot those points on our grid. I know the graph grid didn't come out so well, so just do your best. When x is 1/4, y is -2, so we're down here. When x is 1/2, we're at -1. At our x-intercept, 1, 0, 2, 1, and at 4, 2. Connect the dots. And that is our graph, y is equal to log base 2x. Is it a function? Yes, it is. The domain, directions say to give answers in interval notation if possible, whenever possible. So the domain, remember, is from 0 to infinity. The range, all real numbers, from -infinity to +infinity. Oh, I just remembered, we need to put in our vertical asymptote and label that x is equal to 0. The x-intercept is at 1, 0. Y-intercept, there isn't any, so write down none. Does it have any symmetry? Doesn't have any symmetry. At what interval is the graph increasing? Well, it's increasing throughout the entire interval. So the interval from 0 to infinity, which is its domain, again, not including 0. Is it decreasing anywhere? No, it's not. It is increasing throughout the entire interval. However, it is negative. Underneath, it is below the x-axis between 0 and 1. After 1, when x is greater than 1, this graph is above the x-axis, so that's where the y values are positive from 1 to infinity. Where is it equal to 0? At x-intercept at x equals 1. Find y when x equals 64. That means if we use the equation 2 to the y is equal to x, what is the corresponding y value when I get 64? So 2 to the what power? How many times do I multiply 2 by itself to get 64? That'll be 6 times. You can use that in the calculator. And for what x value is, y is equal to 12, so that means 2 to the 12th is what number? 2 times 2 times 2, again by itself 12 times, will give you 4,096. 14 and 15 are asking for absolute minimum and absolute maximum. Since the graph is continuously increasing throughout the entire interval, there isn't an absolute max and there isn't an absolute minimum. Asymptote, there is that one vertical asymptote at x is equal to 0. Is the inverse of this graph a function? Yes, it is, because our function, because our y equals log base 2x, is also 1 to 1. So therefore, its inverse will be a function. Its inverse, remember we talked about it last class, is the exponential. And it's the equation y is equal to 2 to the x. Remember, we swapped the x and y. Assuming our f of x function, that as x is getting bigger, so as x is increasing here, as x is getting towards positive infinity, what is happening to our corresponding y values? They are also going to positive infinity. However, as x is approaching 0 from the right, so if we go from this side, we're going to 0 from the right. If we're thinking about it from 1 to 0, what's happening to these y values here? They are getting closer to negative infinity. And the name of this graph is called logarithm. So a little bit of warm-up reviewing the graph of a log function. Let's go to the next page where I'm going to talk to you a little bit about how we use the calculator in evaluating logs. First of all, remember from last class common logarithm that when the base is now written, it's understood that the base is 10. Calculators work in base 10 mode as a default because our number system is in base 10. So if you want to press the log button and answer, it will return the exponent that is attached to the base 10 to get the answer. So let's bring the calculator up. And if you haven't gotten yours yet, this is a good time to go get it or take it out of your backpack. Okay. Evaluate to the nearest 10 thousandths. For the first three problems, though, we're going to do those without a calculator. Log 10, basically that means 10 to the what power will give you 10, and that's 1 because 10 raised to the first power gives back 10. 10 to the what power is going to give you 0.001, so we're moving a decimal point over to the left. You know it's going to be a negative number. How many places? 1, 2, 3 to the negative third power, and that will give us 0.001. Log 1, and again, that means 10 to the what power is going to give us 1. And we know that we raise anything to the 0 power, we're always going to get 1. So 0 is the exponent that we're looking for there. And if you want to double check that to see how the calculator works, the log button is over here on the left-hand side. If I want to get log 10, it'll get 1. If I want to find out log 0.001, there's our negative 3. And what's the exponent to which I'm going to raise 10 to get 1? 10 to the 0. So when we do the next two, 4 and 5, log 465, we're going to use a calculator, but we can also estimate a little bit here. 465, since 10 squared is 100 and 10 to the third is 1,000, 465 falls somewhere in between 100 and 1,000, very close to 500, so it should be approximately 2 point something. And since 465, is it closer to 100 or is it closer to 1,000? It is closer to 100, but don't forget, this is a logarithmic / exponential graph. So let's find out what actually is happening here. So if I want to find out to what value, to what exponent I should raise 10 to in order to get 465, now I am anticipating 2 something, and it is 2.667, ... 2.667. So that makes sense, again, because it's increasing faster. Log 0.0865, and again, we want to find out 10 to the what power will give us 0.0865. And we can ask the calculator, what is log of 0.0865? And we anticipated a negative because it's going to be a fraction, just like the one right above it. So negative 1.0630. So again, notice that it's negative. Both 2 and 5 are negative because we have decimals. Those are fraction answers, so we know that's going to be flipped as to a fraction, so it's the 1 over. All right, what if I want to go backwards? And there's the anti-log. Suppose you have the exponent and you want the answer of that exponent raised to the base of 10. It's called the anti-log, and there is a shortcut key on the calculator above the log button. Evaluate n to the nearest hundredth means this is log n is equal to 3.9370, means 10 to the 3.9370 power is equal to what? Is equal to n. So the shortcut key is right above your log button, and because it's in blue, you do your second function key. The 10 is written as the base, and you're automatically raised to the power position, 3.9370. Press enter to the nearest hundredth, 8,649.68. So n is equal to 8,649.68. Now the other way you can do it is just plain old pressing the 10 to the key. So 10 to the negative 1.8765, we can simply do 10 and then to the negative 1.8765, and it's equal to, so notice how the 10 is just a little bit bigger. It's the same thing. This time we get the 0.013, but to the nearest hundredth, it'll be 0.013. Now 3 and 4 are again are different than the 1 and 2. You want to make sure you understand what's being asked of you. In number 3, we're saying n is equal to log 1 over 14. N is the exponent, so it's 10 to the what power is going to give us 1 over 14. And again, realize that the base is 10 because it's not written. So you can just type in log of 1 divided by 14. And we get negative 1.15 rounded to the nearest 100th. So n is equal to negative 1.15. But in number 4, I don't think we need a calculator there. I hope we don't need a calculator there. We write it in exponential form. 3 to the negative 2 power is equal to n. 3 to the negative 2 power is 1/3 squared. 1/3 squared is 1 over 9. So n is equal to 1 over 9. All right, a little bit of review from last class. And let's go to the back, I believe, of this page to start our notes. Actually, not a review from last, a little bit of the 10 stuff on the calculator. New notes for today. We're going to talk about log properties. What you need to remember when we talk about log properties is the fact that log means the same thing as exponent. So when we're talking about log properties, the rules, they follow the same exponent rules with a little bit of a twist. So we have 3 properties here. There's actually going to be a 4th one. We're going to add to it in a minute. Log properties work both ways, so meaning that the left side is equal to the right and right side is equal to the left. The first one is called a product rule. That means that if I have a product of a times b, when I take the log of both sides, the log of n will equal log of a plus log b. Remember that when we multiply bases, we add the exponents. So here we're multiplying the bases, the a times b, and over here we're adding the exponents. I'm going to give you a couple of examples for each of these rules. And we're going to use the calculator to kind of prove it to ourselves that these rules do make sense. They work. Let's use 2 times 4 as the product. And we're going to see if that's the same thing as log 2 plus log 4. According to this product rule, we're supposed to get the same answer. Okay? So let's ask the calculator. Is it true that log 8, which is 4 times 2, which is 0.9030, so 0.9030, is that the same as log 2 plus log 4? Let's find out. Log 2 plus log 4. And what do we get? We get the same answer, 0.9030. 0.9030. It's kind of cool. That again, notice that your multiplication, the 2 times 4, is going to be the same as log 2 plus log 4. Let's see what happens with division. With division says that if n is equal to a divided by b, then I can take that and expand it to a log a minus log b. Okay? Let's see if that works with regular numbers. Let's do 16 divided by 2, and let's see if that's the same thing as log 16 minus log 2. We already know that 16 divided by 2 is 8, and log 8 is 0.9030. So let's ask the calculator, what is log 16, and make sure you close your parentheses, minus log 2. Okay, notice that I am closing my parentheses because you want to make sure that that expression is separated from the next expression. Let's see what happens here. Same thing, 0.9030. Again, kind of cool that that works, but hopefully it makes sense because when we're dividing bases, we subtract the exponents. That's why we're going to be subtracting logs when we're dividing. The third one is the power rule, that if I have an exponent, I can swing it down front, and this is how it works. It's a little bit easier to see it in an example. If I have log 2 raised to the 4th power, what I can do with that 4, I can kind of lasso it and swing it down front, and it now becomes a coefficient. That's going to be the same thing as 4 times log 2. And there really isn't anything I can tie it to in the exponent rules. We can, again, use the graphing calculator to help us prove to us that those are equivalent. So log 2 to the 4th, so it's really log 16, which is 1.2041 ... Is it the same thing as 4 times log 2? 4 times log 2. See if we get the same answer. Yep, we get the same messy decimal, 1.2041. So we have those 3 properties, the product rule, the quotient rule, and the power rule. There is a 4th one that I want you to add to your list, and it's called the equality rule. And the equality rule pretty much says that if log m is equal to log n, then m is equal to n. And it may seem like common sense, but it's always good to write it down, because then we understand that we can ignore the logs and just look at m and n, that if this statement is true, then m is equal to n is also true. Okay. Let's do some examples with properties. Lots of things we can do with properties, lots of simplifying and lots of substitution that we can do. So numbers 1 through 4, we're going to expand using log rules. Number 1, we see that 2 is an exponent. We can bring it down front and rewrite that as 2 times log a. That's the only thing that we can do there. Number 2, log base 5, radical z. Don't forget that the radical, the square root, means the same thing as raised to the 1/2 power. So again, I'm going to bring that down front, and it'll be 1/2 times log base 5z. Number 3, we have a fraction bar. We have the division there. And as soon as I see that, I know I'm going to be expanding it using subtraction. I'm going to have a minus sign somewhere because of that division. And notice I have 3 terms here, the 2, the x, and the y. Since I have 3 terms, I'm going to have 3 logs. Okay? So I'm going to expand. We're expanding. I'm going to expand using my properties. The 2x up on top is going to be expanded using addition, so it's log 2 plus log x. The division is going to be subtraction, and the 3 is going to come out front, so 3 log y will be at the end of my expression. So I expanded multiplication using addition, log 2 plus log x. My division is expanded by subtraction, and then I have 3 log y. Number 4, a little bit more complicated. Notice we have 4 factors now, the 10, the x, and the b, and the c. So I'm going to have 4 logs in my expansion, in my expanded answer. And it's going to be pretty long. So I'm going to start over here on the left-hand side, kind of running into my previous problem. I'm going to erase this. I don't want it to get in the way. I'm going to start out with log 10 plus, because I'm going to be expanding multiplication with addition. This is x to the 1/3. So the 1/3 is going to come out front in front of the x, in front of the log x. Division is going to be replaced with a subtraction. I'm going to put parentheses because I've got more than one factor down at the bottom. In the previous example, number 3, I only had a one factor there, y to the 3rd, so I didn't have to separate it with a minus sign with the parentheses. But this case I do, because my b times c is going to be expanded to log b plus log c. I'm going to clean this up. Log 10. 10 raised to the what power is 10? We know it's 1. 1/3 log x stays 1/3 log x. And I don't have to, but I want to make sure you understand that we can distribute the negative. So if this was a multiple choice question, you knew that those two were equivalent. So whenever we have those parentheses, we can use our properties of distribution to distribute the number that's out in front. So those are examples of expanding. We're going to now go the opposite direction and condense. Still using the log rules. Notice our expressions are longer. We're going to condense to a single log. So here, our answers are actually going to look like our questions in 1 through 4. We're going to go backwards. Start out with writing a single log. And what I can do, I see that subtraction, I'm going to immediately draw a fraction bar because I know there's a subtraction involved, so I know it's going to be changing that to a division. The numerator is always on the left, the denominator is always on the right. So on the left-hand side, I've got a 2 log a, which is going to be condensed to a squared, and my denominator is just a plain old c. For number 6, again, a single log. I'm not going to do a fraction bar because there is no subtraction here. It is only the a that is raised to the 1/4 power, and I'm going to condense addition using multiplication times b. We can also write it as log the 4th root of a multiplied by b. They're both the same. And again, for multiple choice purposes, you want to make sure that you understand that raising a number to a power is the same thing as taking the root of that denominator of the fraction. Last one here, number 7. 1/2 of 3 log C plus log B minus 5 log A. All right, again, it's a single log. Only write down one log, no multiple logs there. I've got a division, so I'm going to draw my fraction bar, and my denominator is fairly easier than the numerator, so I can go ahead and put my denominator. It doesn't matter in what order you write them in. It is 8 to the 5th. Now, what's going on with my numerator? Let's see, I've got a C and a B. The C is raised to the 3rd power. The B is not, but the whole thing has a 1/2 out in front. But so if I bring the 1/2 back up as an exponent, the C to the 3rd times B, all of it will be underneath the radical because it's raised to the 1/2 power. So we've got a couple of examples there using log properties to condense and to expand. On the next page, we're going to do a little bit more expanding, this time with numbers, a little bit less with letters and more with numbers in using our primes. So we're going to rewrite in terms of A, B, and C, given that log 2 is A, log 3 is B, and log 10 is 1. We don't really need that given to us. We already know that log 10 is equal to 1. So again, we're using prime factorization just like we did in the previous unit, log 10 divided by 9, using the numbers 2 and the 3. 10, actually it will stay 10, but 9 can be rewritten as 3 squared. And then using our properties, we can expand log 10 minus log 3. And because it's 3 squared, I can put a 2 out in front, the 2 log 3. Substitution, log 10 can be replaced with 1. And log 3 will be replaced with a b, so it's 1 minus 2b. Same thing with number 9, 60. Let's rewrite 60 using numbers 2, 3, and 10. 2 times 3 is 6. 6 times 10 is 60. So I can rewrite as 2 times 3 times 10. Again, using my properties of logarithms, I'm going to expand multiplication using addition. Log 2 plus log 3 plus log 10. Log 2 will be replaced with the letter A. Log 3 will be replaced with letter B, and log 10 will be replaced with 1. And that's as far as we can go. A plus B plus 1. It's kind of weird. It's different. But again, we're simplifying using our properties, using the primes, and then whatever substitution we need to make according to the directions. 30 divided by 4, log 30 divided by 4, again, using the numbers 2, 3, and 10. 30 will be 3 times 10. And 4, I can write it as 2 squared. Right? 2 times 2. 2 squared. And then I'll use my properties again to expand. Log 3 plus log 10 minus, and then I'll put a 2 out in front because that's the exponent that's going to come down front from the 2 squared. Log 3 will be replaced with letter B. Log 10 will be replaced with 1, and 2 times log 2, which is A. So it's B plus 1 minus 2A. Number 11, slightly different problem, but the same idea. Log base 5a is equal to 2. Log base 5b is equal to 7. Log base 5c is equal to 1. We're going to expand radical a times b divided by c squared to find out what all of that is going to equal. Okay, so we have log base 5, and the a is raised to the 1/2 power, but I'm going to swing that down in front because the exponents come down in front. Multiplication is expanded using addition, so this is log base 5b. Notice they all get a log base 5. Division is going to be expanded using subtraction. The 2 is going to come out front, log base 5c. Now let's do your substitution. Log base 5a is a 2. Log base 5b is going to be replaced with a 7. And log base 5c is going to replace with a 1. So I have 1/2 of 2 plus 7 minus 2. 1/2 of 2 is 1. 1 plus 7 minus 2, a final answer of 6. What else they can do? Numbers 12 and 13. Again, we're going to use primes to simplify our numbers and then do substitution. This time we have log base 3 2 is equal to k. Express log base 3 18 in terms of k. 18 we know is 6 times 3. 6 is not prime, so it's 2 times 3 times 3. That makes sense. 9 times 2, 3 squared. So we can rewrite that as log 2 times 3 times 3, which will be log, I forgot my base 3, 3, 2. And we're going to expand multiplication using addition. And here we could do a little bit more simplifying. We have 3 times 3. There's 2 of them. So I can say there's 2 log base 3, 3. Or you could write it out as log 3, 3 plus another log 3, 3, expanding that multiplication to addition. Or you can, again, like I said, simplify it, writing it as one term multiplied by 2. Log base 3, 2 is equal to k plus, we've got a 2. What is log base 3, 3? That means 3 to the what power is equal to 3? Oh, 1, that's right. Yeah, 3 to the first. So that's a 1. So this is going to be k plus 2. Number 2, log base 3, 2 is equal to k again. This time we're going to simplify log base 3 of 8 over 27. And we can use, again, we can use factors, or we can actually write 8 and 27 both using a base raised to a power. 8 is 2 to the third, and 27 is 3 to the third. We can expand that. The 3 will come out front, so I have 3 log base 3, 2. Division will be expanded using subtraction. So I have 3 log 3 to get 3. We know that log base 3, 2 is equal to k, so that will be replaced with a k. And again, 3 log 3, or log 3 to get 3 is going to be a 1. So we have 3k minus 3. Last two on this page, number 14, log base 5 to get 3 is equal to a. We're going to simplify log base 5 of 75 over 9 in terms of a. 75 and 9, so 75, what are the primes of 75? We know it's going to be 25 times 3. We can either write 5 times 3, or we could do 5 squared times 3. 9, we could do either 3 times 3, or we can do 3 squared. So log base 5, 5 times 3 over 3 squared. Or we can do 3 times 3. And then we're going to expand that. So we'll have log base 5, 5. And I'm going to do the 5 separated. So we're going to expand multiplication with addition. And then expand division using subtraction. And the 2 is going to come out front. Log base 5 to get 5 is a 1. Same thing here, 1. And then log base 5 to get 3 was given to us up in the directions. That's an a minus 2 times a. 1 plus 1 is 2. A take away 2a, a negative a. So 2 minus a. Now some of you may have seen some shortcuts. Again, you could write that 5 times 5 as a 5 squared. Cancel out a pair of 3's would help simplify things, but you don't have to. So there's usually more than one way of simplifying these expressions. It's whatever you see first, and you want to make sure that whatever way you're choosing is the right way. Last one on this page, number 15, log 700 in terms of c. 700, we can break 700 down to 7 times 100. And we don't have to worry about the 100 because hopefully you're now getting better at seeing that log 100 means 10 to the what power is equal to 100, to 2. Log 7 is given to us as a c. So this expression simplifies down to c plus 2. All right, so that's for the notes. Lots of different ways you can use properties. On the next page, on the front and the back, you've got some practice problems. We're going to do the front side together, and whatever time is left in class, we'll do more, you can do more practice on the back. So let's do some practice again, using our properties to either expand, condense, and then we've got some prime stuff that we're doing towards the bottom half of this page. Questions 1, 2, and 3, we're going to expand. Try a little bit on your own. The substitute can pause the video for you to try it on your own, and then in a couple seconds you can turn the video back on to look at to see what the answers are. Number 1, we're going to expand. All of this is multiplication, so we're going to expand using addition. Log 2 plus 3 log x plus 2 log y. Number 2, we've got a little bit of a division there, so we're going to have a subtraction. Log a, 2 out in front, minus, and we have b raised to the 1/3 power, so it's 1/3 log b. Number 3 is a little bit more complicated, and again, we want to make sure you've got 4 factors here, the 3, the a, the b, and the c. So we're going to have 4 logs that are written, and I'm going to actually start this out on the left, a little bit to the left, because I know this is going to be kind of long. This is log base 5. We're starting out with the 3. I've got a plus log a, plus I have a 1/2 log b, and I have that big old 4, and that 4 is going to come out front for the entire numerator. For the entire numerator, that 4 is going to be the coefficient, because the entire numerator, the 3, the a, and the radical b, the whole thing is raised to the 4th power. Division is going to be replaced with subtraction when we expanded it, and then we have a 2 log c. That's not a c. That's a c. The next 2, we're going to go the opposite direction and condense. Again, the substitute may pause the video while you do 4 and 5 on your own, and then play the video again to go over the answers. So for number 4, I see a subtraction, so I know there's going to be a division, and it's a single log. The numerator consists of an a times b, and the 3 out in front means that the entire product, a times b, is raised to the 3rd power, and my denominator is c squared. Number 5, again, a single log, and it's base 7, and I have a fraction bar. The denominator has a b and a c, but the c is squared because there's a 2 out in front, and the numerator is 8 to the 3rd. 6 and 7, we're going to simplify those with primes. Again, try these on your own, and then play the video when you're ready to check your answers. 12 can be simplified as log 2 times 2 times 3, or 2 squared if you would like. So that means that we'll have log 2 plus log 2 plus log 3. Log 2 is an a, another a, log 3 is a b, so we have a 2a plus b. Number 7, log 60 divided by 2. 60, we can rewrite as 2 times 3 times 10, with a 2 on the bottom. And notice what happens. Some of you are thinking maybe the 2's can cancel, and kind of don't cancel them quite yet. See what happens. See if you could have canceled them. See how things go. We have log 2 when we're going to expand using addition. Log 3 plus log 10 minus log 2. Oh, look at that. Yep. The log 2's could cancel even there again if we didn't cancel here. Let's see if that's going to change the outcome of the answer. Log 2 is an a. Log 3 is a b. We know log 10 is 1. Minus a. A's get canceled, left with the b plus 1. So could have we gone back to the beginning and crossed out the 2's? Yes, we could have. And that would have made it a little bit simpler when we needed to condense it. So we can cancel out those 2's because it is allowed. Last 2, 8 and 9, again, work on it on your own for a couple of seconds or with the person sitting next to you, and then play back the video when you're ready to check your answers. Log base 3 of 4 over 9. We can rewrite 4 over 9 as 2 squared over 3 squared. We're going to expand division using subtraction. So I have a 2 log 3, 2, and that's the 2 comes out in front because of the exponent. It's given to us that log base 3, 2 is equal to k. So I will replace log base 3, 2 with a k, and this is going to be minus 2 times 1, so it's a 2k minus 2. Number 9, we have a radical 12. So that means with a 12, I can rewrite it as 2 squared times 3. And because it's raised to the 1/2 power, here I am not allowed to either cancel out a pair of 2's or cancel out a pair of 3's, because this is not really 12, it's the square root of 12. So I have to keep expanding. So that means the 1/2 is going to come out in front. And then inside the parentheses, I can bring the 2 out in front, because I can rewrite that 2 times 2 as 2 squared. So 2 log base 3, 2, plus log base 3, 3, minus, and then inside parentheses, because I've got 2 factors on a denominator, log base 3, 2, plus log base 3, 3. Make sure those are in parentheses, because it is going to change our answer if you do not put parentheses there. Substitution first, the 2 log 3, 2. Log 3, 2 gets a k, so this is a 2k plus 1 minus, inside parentheses, a k plus 1. Distribute the 1/2. 1/2 of 2 is 1, so this is a k plus a half minus k minus 1. K's cancel, 1/2 minus 1, negative 1/2. You should have time to do more work on the back. The back is the same exact as the front, but with different numbers, different letters. So now is a good time again to pause the video and do a little bit more on your own, and then the substitute can play back the video to check your answers. So this one, definitely do problems on your own and then come back and check answers on the video. And I think I'm going to do a little bit less talking on this one and just more writing out the answers so you can check your answers. Okay, number 1. Okay, hopefully this went okay for you. With the time that's left in class, you may begin your day 2 homework, and I will be available after school next week if anybody has any questions about the notes from today. Thanks.